Have you ever pondered what the cosmos is actually made of? According to the cosmological concept, the Big Bang, a tremendous explosion that gave birth to our world as we know it today occurred 13.7 billion years ago. And that enormous blast, everything that has existed was created. Astronomers and physicists have gradually learned a great deal about the universe by discovering stars, stardust, planets, satellites, asteroids, galaxies, nebulae, clusters of galaxies, and other fascinating space objects. Science development has led us to increasingly sophisticated and accurate technology to investigate the cosmos. We formerly believed that our understanding of the distribution of matter across the cosmos was quite advanced, but observations made over the past century indicate that there is still far more to discover. As a matter of fact, all that exists in the universe seems to be much more than what we can detect. The mass we can see and measure is only a minimum fraction of the whole universe, because the larger amount of matter is invisible and undetectable by our instruments. It's like an immense halo that permeates the cosmos without emitting, absorbing, and reflecting nor light, neither electromagnetic wave. This is the dark side of the universe, also known as dark matter. But what exactly is dark matter, and where does it come from? Where can we find it, and how do we know it exists? Keep watching till the end to find out. In 1933, the Swiss physicist Fritz Zwicky was trying to understand the behavior of clusters of galaxies. In particular, while observing a cluster of 1,000 galaxies in the Coma Berenices, 150 million light-years far from here, he found some anomalies in their motion. In fact, they were rotating with a speed about 100 times faster than what the theory expected, as if the total mass of the cluster was about 400 times higher than it was. In other words, the gravity effect of the cluster was too low for such fast orbits. Therefore, Zwicky argued that there had to be much more gravity and more mass than what appeared to keep together these galaxies with those high rotational speeds. The Swiss was the first to use the term dark matter to express that lack of matter. If these observations were confirmed, we will get the surprising result that dark matter is present in larger amount than luminous matter, he said. 6 years later, the astronomer Horace Babcock observed other anomalies in the motion of stars in the Andromeda Galaxy. As a matter of fact, their rotation speeds, while proceeding towards the outskirts, didn't slow down, in contrast to gravitational theory. Nevertheless, so far, this was considered an issue due to a mistake in the process of measurement because of technical limitation. It was essentially believed that the missing mass was made of faint stars, planets, meteors, and scattered gas in interstellar spaces. The turning point occurred at the end of the 1970s when American astronomer Vera Rubin was working on the motion of spiral galaxies and assessed the same thing that Zwicky claimed 40 years before. Rubin and her colleague Ford had studied and measured the rotational curves of about 20 galaxies and had found that moving away from the center of mass, velocities didn't decrease. According to this data, galaxies couldn't stay in balance. They should have flaked off with the outer stars departing for the tangent. There had to be much more mass in there. To understand this concept and explain all of these conclusions, we need to do a short digression about Newton's gravitational and Kepler's laws. Kepler's laws are deducted directly by Newton's gravitation. All rotational systems that can be modeled as a heavy central mass with some smaller and lighter objects orbiting around it can be investigated by applying Kepler's laws. The rotational speed only depends on the distance from the central mass and on the matter amount in the center, and do not depend on their masses. It is therefore expected that, proceeding towards the outskirts, the rotational speed decrease. If this doesn't occur, the obvious way to resolve this discrepancy is to conclude that the mass amount is higher and postulate the presence of non-luminous matter, or dark matter, to balance the system. Nowadays, we have another instrument to assess the amount of dark matter in the galaxies. According to Einstein's general relativity, if we interpose a mass between a distant electromagnetic source and an object that we are observing, since the mass curves space-time, this mass will act as a lens to bend the light from this source. The more massive an object, the more lensing is observed. By measuring the distortion geometry, the mass of the object can be deduced. If the gravitational lens mass is a galaxy, we can get its mass by studying images with the gravitational lens effect. The mass of galaxies calculated with the gravitational lens method is in reasonable agreement with galaxy rotation curves. The amount of dark matter assessed was 10, even 100 times the amount of ordinary matter. Therefore, the universe appeared made up of dark matter with some little amounts of ordinary matter. This was the outstanding conclusions that originally led scientists to deny its presence. Today, we also know that the distribution of dark matter is quite bizarre. Dark matter isn't uniform. What is most intriguing is the halo arrangement around galaxies. If we move from the center towards the outskirts, ordinary matter decreases whereas dark matter increases. The same goes to clusters of galaxies. For example, in the Milky Way, the amount of ordinary and dark matter are comparable. By contrast, outside dark becomes dominant. The universe is like made up of bubbles of dark matter in which galaxies swim like ducklings. According to cosmology, we all know that the universe is born 13.7 billion years ago from a huge explosion, or the Big Bang. Nowadays, we have detected a landmark evidence of the Big Bang origin of the universe, and it's about the cosmic background radiation, or CMB. This was discovered for the first time in 1964 by physicists Arno Penzias and Robert Wilson during radio astronomy and satellite communication experiments. This is an electromagnetic radiation permeating uniformly the universe as a remnant from an early stage of the universe. It is the oldest electromagnetic radiation in the universe, and that's why it's an important source of data. According to COBE satellite, sent into orbit from 1988 to 1993 to measure CMB around the universe, cosmic background radiation is not constant throughout the universe, but fluctuates slightly. In fact, there are colder and warmer areas. These differences are called anisotropies. But why are we talking about CMB? How does CMB relate with dark matter? According to the analysis of this radiation, it was possible to have a precise reconstruction of the mass composition of the universe. According to the numbers, after gravitational lens effects and the spiral galaxy rotational curves, evidence shows that dark matter represents about 80% of the total mass of the universe. But what is dark matter and what is it made of? Over the course of time, many hypotheses have been formulated. At first, this missing mass was thought to belong to invisible stars and gases that could, however, emit radiation. As a matter of fact, there's a lot of mass of this type around the universe, but its amount is far lower than the missing mass, and is not enough to explain dark matter. Then the focus was on MACHO, which is massive, compact, halo, object particles. Non-emitting heavy objects like black holes, neutron stars, white and brown dwarfs. After years of observations, astronomers assessed their effective presence, but their total mass, deducted using the gravitational lens effects, is lower again because it would only represent 15% at most of what we would expect as dark matter. All of these failures led to the formulation of non-ordinary matter theories to justify dark matter. The most popular is WIMP, or Weakly Interactive Massive Particles theory. WIMP particle are massive particle that would interact very weakly. According to the theory, WIMP have still been found in the early stages of formation of the universe, would interact with ordinary mass annihilating, maintaining a kind of balance. At a certain moment, however, because of the rapid expansion of space, these interactions would stop, and by that time dark matter particles have remained unchanged until today. To detect WIMP, if they exist, we have different ways. We can try to reveal them in our particles accelerators, like the LHC of CERN in Switzerland, hoping to observe the energy release when dark matter, in particular conditions, interacts with ordinary matter. Alternatively, we can build ad hoc detectors sheltered from energy interferences and cosmic particles, like the Xenon 1-ton experiment at the Gran Sasso Laboratory in Italy, or the Super Kamiokande detector in Japan. Eventually, we can always hope to detect some WIMP's interaction events with ordinary matter directly in the cosmos by means of our radio telescopes. So far, it should be noted that no WIMP has been detected by any of these huge experiments. Physicists now believe that dark matter is approximately 85% of the whole mass in the universe and represents about a quarter of its total mass energy density. These proportions are quite astounding and flip our point of view on the universe. Matter, as we all know it, represents a negligible and almost ridiculous quantity of the whole mass in the universe. On one hand, more and more exciting discoveries are yet to come, but on the other hand, it's so shocking that all we can see is just a mist in an immensity that we still cannot understand.